A first-order linear differential equation can be written in the form y prime plus p of xy equals q of x. P of x and q of x are continuous functions on an interval. Now, in this video, we're going to do examples where we solve differential equations. But first, I need to derive a function called an integrating factor to help us solve these types of equations. We want to multiply both sides of the equation y prime plus p of xy equals q of x by some function I of x, where I of x is called an integrating factor. This integrating factor will help us solve differential equations of this form. Now, we want to choose I of x in such a way that the left side of the equation y prime plus p of xy equals q of x is the derivative of I of x multiplied by y. That's the idea. So this is what we're going to do. We're going to start with y prime plus p of xy equals q of x. And what we're going to do is we're going to multiply both sides by I of x. So I of x times y prime plus p of xy is equal to I of x q of x. Okay. Now, if I distribute, that says I of x times y prime plus I of x p of x times y is I of x q of x. Now, remember, by design, I of x y prime plus I of x p of x times y must equal the derivative of I of x times y. That's what we need by design. But if I apply the product rule on this I of x times y, because that's what you're doing, you're taking the derivative of the product of two functions, I get I prime of x times y plus I of x times y prime. Okay? Now, what does that mean? That says I of x y prime plus I of x p of x y is equal to I prime of x y plus I of x y prime. But look what happens. I of x y prime cancels out. And what do we get? We get I of x p of x times y is I prime of x times y. Now, let's look at the next page. So that says I prime of x over I of x is equal to p of x. And then you can see I'm going to come over here and I'm going to integrate both sides of that equation with respect to x. That's right here. And so from here, we get the natural log of the absolute value of I of x is equal to the integral of p of x dx plus c. So e to the natural log of the absolute value of I of x is equal to e to the integral of p of x dx plus c. So notice that the integral of p of x dx plus c is the exponent for that e on the right-hand side. And so that says the absolute value of I of x is equal to e to the c times e to the integral of p of x dx. And so I just used the law of exponents that says a to the m plus n is a to the m times a to the n. Right there. All right? Now, what does that mean? That says I of x is equal to ae to the integral of p of x dx. So what I did there was just strip away those absolute values. And notice that a is plus or minus e to the c. Now, we can set a equal to 1 because we just need an integrating factor that works. Could I have a equal 2? Yes, I can. Could I have a equal 1,000? Yes, I can. A equals 1 is just 1 for convenience. And so the integrating factor, I of x, is equal to e raised to the integral of p of x dx. And that's how we derive that integrating factor. And with that in mind, let's do some examples. So the directions say to find the general solution of the given differential equation. Okay? So let's do it. Now, from here, let's take a look at example 1. So on example 1, we have the following. Suppose y prime plus y is equal to x e to the negative x plus 1. Now, my p of x is the coefficient of y. It's the value being multiplied by y. In this case, it's equal to 1. So my integrating factor I of x is e to the integral of 1 dx, which is equal to e to the x. So what I'm going to do is multiply both sides by e to the x. So e to the x times y prime plus y is e to the x times x e to the negative x plus 1. Okay? Now, this says e to the x y prime plus e to the x y is equal to. Now, if I multiply, I got to distribute that e to the x to each term within the parentheses. And so I'm going to get x plus e to the x. E to the x times 1 is e to the x. Now, I want you to notice something. The derivative of y is y prime. That's over here. The derivative of e to the x is equal to e to the x. And so it's no accident. I'm going to write this as the derivative of e to the x times y prime on the left side. On the right side, we get x plus e to the x. So what does that say? That says e to the x times y is equal to the integral of x plus e to the x dx. Okay? So e to the x times y is equal to 1/2 x squared plus e to the x plus some constant c. So I'm going to solve. So y is 1/2 x squared e to the negative x. And don't forget, e to the negative x is equal to 1 over e to the x. Okay? And then if I take e to the x divided by e to the x, I get 1. So I'm going to put a 1 there. Plus ce to the negative x. And that's the solution to example 1. And with that, let's take a look at example 2. Suppose I give you the following. Suppose y prime plus 2xy equals 2x e to the negative x squared. So I'll write that a little more clear. Now, p of x is equal to 2x, okay? So now I need an integrating factor. So I of x is e to the integral of 2x dx, which is equal to e raised to the x squared. And so let's multiply both sides by e to the x squared. So e to the x squared y prime plus 2xe to the x squared y, that's the left side. On the right side, I get 2xe to the negative x squared times e to the x squared. So it works out really, really slick. Notice on the right side, I get 2x. On the left side, I want you to really pay attention to what happens. Notice that the derivative of y is y prime. The derivative of e to the x squared by the chain rule is e to the x squared times 2x, or 2x e to the x squared. So remember, this integrating factor allows me to write the left side as the derivative of a product. And that product, notice I'm going to take e to the x squared from the first term, and I'm going to take y from the second term. And that's exactly what you get. So it's the derivative of e to the x squared times y is equal to 2x. And so from here, e to the x squared times y is the integral of 2x dx. And so e to the x squared times y is x squared plus c. And so if I solve for y, I get x squared e to the negative x squared plus ce to the negative x squared. And then this is one of those you want to double check with your instructor as to how they want you to express your solution. You know, sometimes the instructor may want you to factor out an e to the negative x squared, and you get x squared plus c in parentheses. Or you don't want a negative exponent, and so your instructor might want you to write this as y equals x squared plus c divided by e to the x squared. So it's one of those you want to check with your instructor on how the solution must be expressed. All right, now I want to do a problem like this. So we'll call this example 3. Suppose we had xy prime plus 2y equals sine x. And notice that x is greater than 0. Okay? We can't have x be 0 or this doesn't make sense. Now, I want you to look at the coefficient of y prime. The coefficient of y prime, or what's being multiplied by y prime, is not 1. In other words, notice how this differential equation is not written in the form y prime plus p of xy equals q of x. It must be written in this form for us to look at the integrating factor. And so what I'm going to do first is I'm going to divide both sides by x. So when I do, I get y prime plus 2 over xy is equal to sine of x divided by x. Now I'm allowed to get that integrating factor. So notice that p of x is equal to 2 over x. So I of x is e to the integral of 2 over x dx. And so this is equal to e to the 2 times natural log of x, right? X is greater than 0, so I don't have to worry about absolute values. And so this is e to the natural log of x raised to the second power. But that's equal to x squared. So what do I do from there? I'm going to multiply both sides by x squared. So x squared y prime plus 2 over x times x squared y, okay, is equal to sine of x over x times x squared. And we'll say over 1, okay. Now, this says x squared y prime plus 2xy. That's on the left side. On the right side, we get x times sine of x. So I hope that's okay. Now, watch what happens. The derivative of y is y prime. The derivative of x squared is equal to 2x. So remember, this is the derivative of some product equal to x times sine of x. But the question is, what goes inside here? Well, I need to borrow y from the second term, and I'm going to borrow an x squared from the first term. So this is the derivative of x squared times y, like so. So this says x squared times y is the integral of x sine of x dx. And this is just a classic integration by parts problem. And so what I'm going to do is I'm going to let u equal x, and dv is sine of x dx, like so. So du is 1 dx, and v is negative cosine of x. And so x squared times y is uv, which is negative x cosine of x, minus the integral of v du. So I think about it like a zigzag. And I'm going to write negative cosine of x dx. So x squared times y is negative x cosine of x plus the integral of cosine of x dx. So x squared y is negative x cosine of x plus sine of x plus some constant c. Okay? And then all I have to do is solve for y. So y is, let's remind ourselves, I'm going to get negative x cosine x over x squared. Plus sine of x over x squared. Plus c over x squared. And again, it depends on your instructor and how your instructor wants this written out. So it's one where you want to verify. And so one possibility is you can write this as negative x, y equals negative x cosine of x plus sine of x over x squared plus cx to the negative 2. Or they might have you just write this, the sum of the numerators all divided by x squared. But it's one thing you would want to check with your instructor as far as how your instructor wants you to write the solution to this differential equation. So I will leave that in this form. But again, it's something you would want to check with your instructor on. Now, let's do another one. Suppose I ask you the following. We'll call this example 4. Suppose 1 plus x squared y prime plus 4xy equals 1 plus x squared raised to the negative 2. Now, I need to divide both sides by 1 plus x squared. So y prime plus 4x over 1 plus x squared y is equal to, and then we're going to write this as 1 plus x squared to the negative 3, if you don't mind. Because think of 1 plus x squared to the first, right? So that'll be 1 plus x squared to the negative 3. Now, p of x is 4x over 1 plus x squared, okay? Now, I'm going to show you something here. I'm going to write this as 2 times 2x divided by 1 plus x squared. Now, you might ask, well, why would I do that? Because in my mind, I'm looking at the denominator, and the derivative of the denominator is 2x. So, and I just happen to know 4x is 2 times 2x, right? So my integrating factor, I of x, is equal to, now this is going to be e to the integral of 2 times 2x divided by 1 plus x squared dx. Okay? But this is e to the 2 times the natural log of 1 plus x squared. And this is e to the natural log of 1 plus x squared, all raised to the second power. So therefore, I of x is equal to 1 plus x squared, all raised to the second power. Do not square that out. Leave it as is. Now, what goes on from there? So let's go back and we're going to write our differential equation. So let's just kind of remind ourselves. Y prime plus 4x over 1 plus x squared, and this is times y, is equal to 1 plus x squared raised to the negative 3. And so that says 1 plus x squared times y prime plus. Now, what I get is 4x times 1 plus x squared times y. That's the left side. And on the right side, we get 1 plus x squared to the negative 1. So what I did was I multiplied every term by 1 plus x squared to the second power. So this is what I claim we get. Now notice that the derivative of y is y prime. The derivative of 1 plus x squared to the second is this. Okay? And so I get 1 plus x squared to the second times y. This whole thing prime is 1 over 1 plus x squared. That's the same thing. Okay? So 1 plus x squared times y is the integral of 1 over 1 plus x squared dx. And we're almost done. So 1 plus x squared to the second times y. Well, that's just arctangent of x plus c. And pretty much I'm done. So this says y is arctangent of x plus c divided by 1 plus x squared raised to the second power. And that'll conclude this video. And This is for a differential equations class, or it can be for a calculus 2 class. We talked about first order linear differential equations. We looked at 4 examples, and then on top of that, we derived the integrating factor. So, okay, thank you.